All right, so we watched that last big video that walked us through one of these huge problems, and so now it's going to be your turn to kind of try it on your own with a little crutch called Mr. Foster. So I'm going to be helping you walk through this problem, but again, I want you to kind of try and take the lead using the video pause feature. So try and get ahead of me, and then if you feel like you're getting stuck, and then watch a little bit more of the video. If you feel like you're getting it all the way through, just keep going and wait till the very end to check your answers, okay? All right, so let's get started. First thing we're gonna do, we're gonna check that side video one more time just to make sure we know what we're looking for. So you need a refresher on the rules. Let's refresh them quick. If you don't, just skip ahead a little bit. So when we want to reduce a circuit, we want to smoosh those parts together. The first thing you need to do is draw your circuit, identify your nodes. Your nodes are these places where you have 3 or more wires coming together. So identify those nodes. I like to just circle them in green here on the board. Step 2, you need to look for series. So yes, I say step 2 and step 3, and it is this order very much. Always look for series first, parallel second. So we're going to look for series. Series is when I have multiple resistors between nodes. So I might take this upper path and I hit 1 resistor, 2 resistors before I get to the next node. Yes, those two are in series. When I go down this path, there is only 1 resistor along that path, so that is not a series. So whenever I identify a series, I need to combine or smoosh those together. So I would take those top 2 and I need to smoosh them together into a single resistor. Whenever you smoosh, whenever you combine, you always want to go back to step 1. You want to redraw that circuit. Identify the nodes. Some of those nodes may have disappeared, and they definitely will disappear when you're doing parallel combinations. So you go back to step 2. Are there any multiple resistors along a single path? Nope. The reason I say is do step 2 again, sometimes you miss a couple. So sometimes there might be 3 resistors in series, you only saw 2 of them. So just go through that one step again. Step 3, we're looking for parallel this time. That means we're looking for multiple paths with only 1 resistor per path. And this is between nodes. So when I go from this node to this node, I can either go up, only 1 resistor on that path. I can go down, only 1 resistor on that path. In that case, those two are in parallel, so I need to combine or smoosh them together into a single resistor. All right, now that we've watched the side video, let's go ahead and give you a chance to start it out. Try and see what you can smoosh together, all right? All right, so we've paused. Let's take a look. So from my perspective, I see my nodes here, here, and here. I'm looking for, first of all, series. So I'm looking for multiple resistors on a single path between 2 nodes. So that would be those 2. When we run into a situation with multiple nodes here, don't think that you can go multiple, multiple, and count all of those in series. It went through in nodes. Your path starts and ends at a node. There are no nodes along a path, okay? So first thing I'm going to want to do is put those 2 together using series. All right, so let's go ahead, redraw that, see what we get. All right, I jumped ahead a little bit here on you. So we are going to see not only does that series combine, but the next step, we're going to see those resistors combine in parallel. We moved on to step 3 of that side video. We've combined them in parallel, and now we have this single 3 resistor circuit. They're all going to combine in series to be the total. Now, once I snap my fingers next, we're going to see the whole bottom. So let's go ahead and check that out. Wow, what a doozy here. Okay, so a couple things I noticed before I filled it out. I forgot to write these in the proper format with the inverses when I added them. And when I added those 2, I should have got 3, not 2. All right, so I'm going to stand over here, give you a second to pause it, check out and make sure you got all those answers, and then I'm going to walk through it. All right, so let's walk through it. So the first step before I snapped it was you needed to combine these 3 resistors, RB, RC, and R6 in series. They combine together to be 7 ohms. We then use the Ohm's law to figure out how much current is running through that one resistor. Now, because these three combine together in series to be this resistance, all three of these are going to have the same 2 amps flowing through them because they're in series. So I'm going to step back with that current being the same. So RB, RC, and R6, all in series, are all going to have the same current as the one they combine together to be. So I use Ohm's law and that same current of 2 and their individual resistances to find their individual voltages. Now, because they're in series, I should be able to add those voltages up to get the total voltage of 14 volts. Stepping back one more, using parallel this time. Now, when they're in parallel, they're going to have the same voltage. So the voltage RC has is going to be the same as the voltage R4 and R5 have. That's their link with parallel. All right, so I need to look at the voltage for RC, which was 4 volts, apply that to R4 and R5. So I apply that 4 volts in here and solve for the current in each of them. Amp each. 1 amp, 2 amps. Is that what I had in RC originally? Yes, 2 amps. And that's because I have my 2 amps that comes out of here, it splits, comes back together. I got 2 amps, comes around here, splits. I got 1 amp, that's 2 total amps flowing. All right, so let's see how it splits through RA and R3. All right, again, RA and R3 are going to have the same voltage as the one they combine together, RB. So I look at the voltage for RB, 6 volts. Move that RB back. Okay, so RA and R3 are going to have the same 6 volts. So I plug that into Ohm's law, solve for their individual currents. I have 0.5 amps and 1.5 amps. Combine them, 2 amps. So in this case, they didn't split evenly. We had more current go through the 4 ohm and less current go through the 12 ohm. That makes sense. Path of least resistance. It's easier to go this way, so more current flows this way. All right. Now we're going to make one more step back, and that's using RA. So RA was made using series. So RA is going to have the same current as R1 and R2. So I find the current in RA, 0.5 amps. Bring that back to R1 and R2. Plug that 0.5 amps in and solve for those V's. 2.5 volts, 3.5 volts for a total of 6 volts. Is that how many volts I had in RA? Yes, so it checks out. And that's how you deal with these problems. They need a lot of space. You need to be very particular and keep track of everything. Don't try and rush it, okay? We got plenty of time. Work the problem out. Write everything out, okay? I've shown you a pretty good organizational pattern here. Try and follow it or find one that works for you. All right, oh, one other thing actually. I get a lot of questions about a choice I made here. So I made the choice to do a series, and I didn't combine these two, even though they were in parallel first. And that's because of that side video. I like to always, once I've done one combination of series, I like to always do series first. If I find anything in series, I combine it, okay? Then I move into a step where I'm looking for basically anything in parallel because I've combined everything that's in series. And so that's, whenever I do these combined steps, I like to have the common things, parallel, parallel. All of them that are in this step of combination are parallel, just to keep things a little more consistent. So I know I'm always bringing back voltage here. Okay, now I'm always bringing back current there.